Hey, it's Mr. Springer. Trying to give you some help on that big packet so that I'm sick and can't get to school today or yesterday. I was at training on Friday. So here we go. The big thermochemistry AP packet. There's 12 problems on there. Let's give it a whirl. Number one, it talks about Q is 15.6 kilojoules and W is 1.4 kilojoules. We use the equation delta E equals Q plus W. What we need to look at is what does it say about both the Q and the W. In this case it says that heat was absorbed. That makes Q positive. And work was done on the system makes W positive. So they're both positives. And when you're doing thermochemistry, if it's positive, you should write positive. And if it's negative, you should write negative. So we know for sure that you know what you're talking about. So 15.6 plus 1.4, no big deal. Number two, this was a P delta V problem. Work is negative P delta V. The negative on the P delta V, you figured that out when you read the chapter or maybe when you read this big packet. It's explained at least one of those places. I know in the textbook it is. But anyway, we got 46 liters changing to 64 liters. So that gives us a delta V of 64 minus 46. It ended at 64. It started at 46. The change was 18. Pressure is 15 atmospheres. W equals negative P delta V, which is negative 15 atmospheres times 18 liters. And your units on that are going to be liter atmospheres, or atmospheres liters. That's the one usually people say. And we'll have to correct for that later. Number three, we're going to put both of those equations to work. We know that delta E is Q plus W, and W is negative P delta V. So delta E is Q minus P delta V. They gave us a correctional figure in there, 101.3 joules per liter atmosphere. This is going to P delta V. Remember, it was in liter atmospheres, so that will cancel out the liter atmospheres in the problem. It went from 4 times 10 to the 6 liters to 4.5 times 10 to the 6 liters for a difference of 0.5 times 10 to the 6 liters. And it said that Q was 1.3 times 10 to the 8th joules. They called it heat. That's how we know it's Q and not anything else. And so we're going to plug in there 1.3 times 10 to the 8th joules minus 1 atmosphere times 0.5 times 10 to the 6 liters times 101.3 joules per liter atmosphere. Notice your atmospheres cancel, your liters cancel. We got joules. Now we can combine those. Everything will be hunky-dory. Is that something you've heard before? I don't know. Number four, we're turning solid potassium hydroxide into aqueous potassium hydroxide. Probably going to add water to make that happen. In the process of adding the water to the 14 grams of potassium hydroxide, it has 43 kilojoules per mole given off. That's your delta H figure, which is your heat term. If it's giving off heat, is it going to feel warmer or colder? Well, it's going to feel warmer. Does that mean it's endothermic or exothermic? Well, it's giving off heat, so that's exothermic. Sorry about that. 14 grams. That's the molar mass to get it into moles. Times 43 kilojoules per mole. Right, so you got moles, we got grams canceling, you got moles canceling, just be left with kilojoules. And they say you want it in kilojoules per mole reaction for some reason. I haven't read that article. Number 8, moving right along. They give us an initial and a final temperature. We can find delta T from that. If it ended at 31 and started at 24, you subtract, you get 6.7. Both of the solutions were 100 milliliters at 1 molar solution. The density it gave us as 1 gram per cubic centimeter, which is the same as 1 gram per milliliter, which means it's mostly water. And that C is also the specific heat of water, 4.184 joules per gram degree Celsius, or constant P. So negative Q equals delta H. So 200 grams, because there's 200 milliliters, two 100 milliliter solutions, 200 grams, 4.184, 6.7 degrees. Make it negative at the end because it's exothermic. This is actually Q, so make it negative, make it delta H. Combustion of methane, which is natural gas. We got 5.8 grams of that. Hopefully you know that's going to give off heat. When you burn gas, it gives off heat. Molar mass of the methane, 1605. take the 5.8 grams, divided by its molar mass, times negative 890, because that's kilojoules per mole. That's a negative sign. I don't know if you can tell it or not. So H is going to be something negative. Number 7. This used, that's the same problem. Okay, so barium nitrate and sodium sulfate solutions, 1 liter times 1 molar. So each one is 1 mole. We got 1 liter of each and 1 molar of each. So that's 2 liters for, or 200 or 2,000 grams, 2,000 milliliters. It'll be 2,000 grams. So we got 1 mole of each. So we make 1 mole of product because it's a 1 to 1 to 1 to 2 ratio. It says that it's mostly water, so 4.18, and the density was about 1 gram per cubic centimeter. That's how we know it's 200 grams or 2,000 grams. Delta T 28.1 to 25 went up by 3. So 2,000 grams, 4.18 joules, 3.1 degrees Celsius will make it negative because we know it's exothermic. Because temperature went up. Temperature went up. It's exothermic. It's exothermic. Do the math. Make it negative. Number 8. That funky looking E is the Greek letter sigma, which in math it means the sum of, not some of, but sum, like addition. Sorry. Aluminum solid is what we expect it to be. It has a delta H value of 0. They gave you the ammonium perchlorate as 295 negative. We got to multiply that by 3. Aluminum oxide solid, negative 1676. It's on the chart. Aluminum chloride solid, negative 704 kilojoules on the chart. 3NO gas, 3 times 90 would be 270 kilojoules. It's positive this time. 6 times negative 242 is negative 1452. So we're going to take all these negative, or all these on the right side, add those together. Subtract off the left side. It's negative. It's minus a negative, it's just plus a positive. And it looks like this side is going to be way more negative than this side is, so the answer is probably going to be negative, but you can do the math to find out. Number 9. We did this problem the other day, only I gave you the figure for X. This time we want to know what X is. Remember the O2, again, oxygen made out of oxygen is just 0. 6 times the CO2 number, it's on the chart. 6 times the H2O number is on the chart. 2800 is, that's the delta H at the end. It's negative because it's the product. Negative 2800 equals negative 2361 minus 1714.8. All that together minus X. Solve for X. Simple algebra problem. Give you a hint. I'd take the X over here and bring the 2800 over here. That's what I would do. Number 10. Sorry. 2 aluminums. We're making aluminum out of aluminum at 0. Fe2O3 minus 826 on the earlier chart. Al2O3 negative 1676 on the earlier chart. Iron, again, a 0. So we're just subtracting 1676 negative minus negative 826. Let's see what you got. Probably got to be a negative number around 850. Number 11 is a very unusual question to start showing you how to do these problems on. Well, let's give it a whirl. They in the problem had put this equation at the top and then these 3 listed together. I like to put it at the bottom. I've got to turn these 3 equations into this one. Okay, so what I want to do is I want to make sure that if it's on the left down here, it ends up on the left up there. If it's on the right down here, it ends up on the right up there. You can reverse reaction, you can multiply by something, but whatever you do to the reaction, you do the same thing to the delta H. Excuse me. So in the product, and the final, I've got H3BO3. I've got 2 of those. Up here, the only place that shows up, there's only 1 of them. So I'm going to multiply this whole top by 2, including this. It's actually kilojoules per mole, I believe. Okay, now that screwed up some of this other stuff. Don't worry, it'll come back. Alright, now I've got B2O3. The only place that shows up there is right here, but it's 2. How do I get from 2 to 1? I'm going to divide by 2. let's see, 17.5 divided by 2. On a normal day I would do that in my head, but today my head is full of mucus. 8.75. So that's now a 1. That's a half. That's a half. Here we've got a H2B4O7, a whole one. Here we got a half one. It doesn't show up anywhere down here, so that's going to have to be flipped so it'll cancel. Plus the HbO2, which I have HbO2 there. HbO2. Anyway. And it's 2 there, and it's 4 here, so I've got to flip that to make that cancel. And I'm going to divide by 2. And flip it. So it turns out to be 2 HbO2s. I forget what is it, AQ. Makes 1/2 H2B4O7 plus 1/2 H2O. And since I flipped it, I got to change the sign. So now 11.3 is positive. Divided by 2, 5.65. And this is all gone now. Sorry. So my half H2B4O7s are going to cancel. My 2 HbO2s are going to cancel. So bring it down. Nothing. The only thing on the left, 2 H3BO3s. On the right, you've got 1 B2O3, and we got 2 and a half, which is 3 waters. So now I just have to add these all together. Negative 0.04 plus 5.65 plus 8.75. Okay, it's around 14.4 kilojoules per mole reaction. One more problem. This is the easiest one. If you know that the H2 actually has an H bonded with a single bond to another H, and your F2 is F bonded with a single bond to the other F, and an HF is always a single bond. And we have 2 of those. Alright. These bonds have to be broken. These bonds are being formed. Breaking bonds is endothermic. So those are positive. Making bonds is exothermic. So negative. So positive 432, positive 154, minus 565, minus 565. Like that. Okay. So hopefully this helps. Then there are some questions at the end that you can probably do. Just look at the graph. And most of them are right there in the graph. Hopefully I'll see you tomorrow.